Okay, so let's continue. And this is part 2.8, and that's sign part 2. So my goal is to prove existence of a homomorphism with the properties as stated. And for this I need a definition, which is a very important one. So let's consider a permutation sigma in Sn. And let's take a pair of indices ij from 1 to n. So, and then here is a definition. So we say that pair ij, I can maybe think of it as a set with two elements. Ij is an inversion for sigma, so in sigma, if either I is less than j and sigma of I is bigger than sigma of j, or I is bigger than j and sigma of I is less than sigma of j. So the idea is that inversion means that somehow we had two indices going in some direction and our permutation exchanged their ordering. So let's do some examples. So you can take a permutation 1, 2, 3, 4, 5, going to maybe 3, 5, 1, 2, 4. And then for each pair, you can think what happens. So let's just write down all inversions. So we can look at just all possible, pairs. 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 4, 2, 5, 3, 4, 3, 5, and 4, 5. And let me label which of them are inversions. So 1, 2, when you look where they go, 1, 2 goes to 3, 5, and what it means that 1 was less than 2, and sigma of 1, which is 3, is less than sigma of 5, which is of 2, which is 5. And so it means that basically the order of 1 and 2 is the same here. Okay, so this is not an inversion, and then 1, 3 goes to 3, 1, and this is where we have the switching. So 1, 3 is an inversion. And 1, 4 goes to 3, 2, and 1, 4, 1 is less than 4, but 3 is bigger than 2, so 1, 4 is an inversion. And 1, 5 is not an inversion. 2, 5, 5, 4 is an inversion. 2, 4 is an inversion. 2, 3, 2 is less than 3, 5 is bigger than 1, it is an inversion. 3, 4 is not an inversion. 3 and 4 and 1, 2 goes in the same order. 3, 5 is not an inversion. 4, 5 is not an inversion. So 1, 2, 3, 4, 5 inversions. Okay, so how to count this number of inversions, how to think about it. So there is a very nice way to think about it, kind of more topological if you wish. So let me just rewrite this permutation once again, and I will just make it slightly bigger here. And then, I mean, after all, this permutation just defines a map. Let me draw the set twice, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And then what I want to do, I want to use colors, or maybe still this, to show where each of elements go. So I just want to present sigma as a map. I just want to draw it pictorially. So 1 goes to 3, 2 goes to 5, 3 goes to 1, 4 goes to 2, 5 goes to 4. And then my claim, which is really easy to see, is that number of inversions is just number of crossings of this diagram. So crossings mean this is a point where two segments cross. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You can check that. So 2 and 4 is an inversion, for instance, because here is a crossing. And 1 and 3 is an inversion. So, of course, that's completely obvious, because if you look at just two elements, I and j, they are somewhere here, let's assume I is less than j, then crossing means j is less than I, and so it exactly means that the corresponding arrows will cross. And if sigma of I is going in the same order as sigma of j, they will not cross. So this is obvious, but to make this completely precise, you need to explain what you mean by this diagram. And formally speaking, you should be careful. You need to say that, okay, you just write down these numbers, that's fine. Then you draw arrows, and you want these arrows to be, not crossing, so that there will be no 3 arrows crossing in the same point, for instance. You can draw them arbitrarily. They don't need to be exactly straight, but you want them to be organized kind of going from up to down, and also you can move them slightly so that never 3 arrows intersect in one point, and you need to go to topology course to be able to make this completely precise. Then you can actually use it as a definition. So algebraic definition, as it happens very often, is much simpler, though actually computing number of inversions is easier here. And I will just use notation inv of sigma. This is just number of inversions. Number of inversions. Okay, so now I'm going to give the following definition. So remember, I'm proving existence, so I just need to say what my sign is. So define sign of sigma equal to -1 power the number of inversions. So what it means, it will be -1 if number of inversions is even, and is odd, and 1 if number of inversions is even. So let me write that down. So it will be 1 or -1, and this is inv of sigma is even, and this is when number of inversions is odd. So here there is no question whether this definition makes sense. It's just uniquely defined number, you can say that. But of course, a non-trivial fact is that sigma is a homomorphism. So the fact it's surjective is obvious, because you can easily take transposition 1, 2 goes to 2, 1, and it's easy to see that there will be just one inversion, 1, 2. So there exists this odd permutations, but it's not clear that it satisfies this property sign of sigma times sign of tau is sign of sigma tau. And you might think, oh, but it's -1 power number of inversions. Maybe when you multiply permutations, inversions just add up. And sometimes it's exactly what happens, but not often. For instance, you can look at a permutation which sends 1, 2, 3, 4, 5 to 5, 3, 4, 1 to 1, and you will see that basically every pair is an inversion. So there are choose 2 inversions, but obviously your permutation, if you just square it up, you will have a permutation with smaller number of inversions, and so they cannot add up. So something more interesting happens. And next, let me actually find. Let me actually prove it. So proof is based on a very beautiful idea, and there are two ways to present this idea, kind of with polynomials, without polynomials. I will do both, but mostly emphasizing maybe the one with polynomials, but rephrasing it without them as well. Okay, so let me do it right now. Okay, so now I need to show that sign is a homomorphism. So for this, I will use a very interesting trick. I will use polynomials. So let's take x1 and so on, xn, some variables. So these are some variables. And you can think of them as just, as usual, kind of variables commuting with each other, and we will look at polynomials in these variables. Formally, we will discuss it next quarter. So then I want to formulate the following lemma. So lemma. And lemma is an explicit formula for, so let sigma be some permutation in Sn. And then lemma is some explicit formula. Lemma says -1 power the number of inversions of sigma is equal to product over all pairs I, j, I not equal to j, and of course I mean less or equals than n, greater or equals than 1, and then I write x sigma of I minus x sigma of j divided by xi minus xj. So formally speaking, this is a rational function, and I multiply rational functions in many variables. If you're confused with that, you can just think of x1 and so on, xn as just any distinct numbers, real numbers, for instance. It doesn't matter at all here. But next quarter we will discuss these polynomials in great detail. So what stands here is a product, and it means you multiply these things. Pairs ij means you just take all pairs. And just the set of indices here, so number of pairs is of course n choose 2. And you might say, but wait, for every pair I can take I less than j or I bigger than j, they represent the same pair. But it seems that the problem is not well defined, but actually it is, because if you exchange I and j, you simultaneously change sign here and there, and so the expression doesn't matter, doesn't change. So let's do some example. So example is just take a permutation 1, 2, 3 goes to 2, 3, 1. And then what you look at here, so we need to choose pairs, and pairs will be 1, 2, 2, 3, 1, 3, and there are 3 pairs like that, and so we just write x1 minus x2, and on top sigma of 1 is 2, sigma of 2 is 3, and I get x2 minus x3. And if I choose accidentally to change the order, I said let's take pair to 1, I will get here x2, x1, and here x3 minus x2, and the fraction is the same because both of them will switch sign. So x1 minus x2, x2 minus x3, and here I will have x3 minus x1, and finally x1 minus x3, and on top I have x2 minus x1. And you can see that basically I have the same brackets up to sign, and this cancels out, and 1, 2 to 1 kind of cancels out, but I get a -1 sign. 1, 3, 3, 1 cancels out, I get a -1 sign, and so this equals to 1. And this is exactly what I expect, because my permutation is even, number of inversions here is equal to 2. And actually, exactly 1, 3, and exactly 1, 2 are inversions here. So if I draw this little diagram here, I will get, so 1, 2, 3 goes to 1, 2, 3, and this is 1 goes to 2, 2 goes to 3, 3 goes to 1. So there are 2 inversions, and these are exactly these 2. Okay, so this is an example, and how would I prove that? So proof is very, very simple. So proof is that if I just look at monomials. So let's look at set of monomials, and elements of the set will be these monomials, but up to, up to sigma of I minus x sigma of j up to sign. So this set is basically, it has a number of elements, is a number of pairs ij. So cardinality is n choose 2 elements. And this is just the same set as set of this plus minus elements xi minus xj. So simply because, okay, if I use sigma, sigma is a bijection of sets, so it's definitely a bijection of pairs of elements there. And so, of course, this is a bijection between my two sets. And so set of monomials is the same, so it means up to, if you look at them up to sign. So the product will definitely be equal, so this product is definitely equal to plus or minus 1. And then the sign depends on how many of those xi minus xj switch sign when you do when you apply sigma. And this is of course just the number of inversions. So eventually you get that this is minus 1 power the number of inversions. So I don't want to be too pedantic here because we have not yet discussed polynomials, but that's actually a very, very nice proof. And this gives a formula for minus 1 power the number of inversions of sigma. And now let me erase this part and I will keep a formula for a second, and I want to show that this number is actually, this gives a homomorphism. So I will just erase this part. So, okay, so let's take sign of sigma tau for two permutations. And then this is just product over all pairs. And then I have x sigma of tau of I minus x sigma of tau of j divided by xi minus xj. And the idea is that actually I can divide and multiply by x tau of I minus x tau of j, and then since it's a product and everything commutes, I can write it down as product of two products. So I will get a product over all pairs x sigma tau of I minus x sigma tau of j divided by x tau of I minus x tau of j and times product. And again, so everything is commutative. It's actually just plus minus signs everywhere, so it's not terrible. Product x tau of I minus x tau of j divided by xi minus xj. So this is also over the same set of n choose 2 pairs. And then, so this is of course just sine of tau. And this thing looks a little bit more complicated, and we have this double sigma tau composition here. But just think a little bit, think about that in the following way. So you have a bunch of elements you multiply, and multiplication is commutative, you can permute them. So an idea is that actually tau is a bijection, and you know that this thing depends only on the pair of elements, not on their order. And tau is a bijection on the set of indices, so tau gives a bijection on the set of pairs. If you apply bijection to a product, to every element, you will get them permuted in some way, but you will get the same product. So this is why it equals to product over all pairs of x sigma of I minus x sigma of j divided by xi minus xj. And again, algebraically, the idea is that tau is, if you look at the set of pairs ij, just subsets of size 2 of the set of our indices, then tau is a bijection from the set to itself. I mean, it relabels elements, it will relabel the pairs, it is a bijection. And so if you apply tau, so this is a product over all pairs ij, but you can say also it's a product over all pairs tau of I tau of j, and then clearly this is the same thing. So that's actually a proof. And this is, of course, this is sigma of sine of tau, and this is, of course, sine of sigma. And so we get that sine of sigma tau is product sine of sigma sine of tau. So there is another proof of that. You can do it without polynomials, and actually we have not used polynomials much. So we never used anything except that whatever commutativity of multiplication and things like that. But firstly, that's really good to remember this formula. We will see it once again next quarter when we talk about discriminants and stuff like that. And such products appear a lot in algebra. But also it's a nice exercise to rephrase all of that without talking about polynomials. Okay, finally I want to make a quick remark about determinant and sign. So, by the way, here we proved this theorem about the fact that sign exists. So there exists a homomorphism with these properties, and given by this formula if you wish. So this is sine of sigma, and we know that, because we know it's unique, we now know that it equals to the number of transpositions in any decomposition of your permutation into product of transpositions. Okay, I want to end all this section 2 with maybe just reminding you definition of determinant. So if you have a matrix and you want to compute its determinant, and the matrix is maybe A11 to ANN, then there is this formula for determinant. Maybe you have seen it already. So it's a sum over all permutations in the group Sn. And then you take, in our definition, it will be just sine of sigma times A1 sigma of 1, and so on, An sigma of n. And a nice way to think about it is that basically you take sum, you have a matrix. So this thing corresponds to the following picture. You take your matrix, and then you choose, so 1 sigma of 1, and so on. It's just kind of a choosing one position in every row and in every column. So if you play chess, you can think of it as rook positioning. So you have a chessboard, and you want to position rooks so that in every line and every horizontal and vertical lines, there will be exactly one rook kind of firing there. And so number of terms here is a number of ways to position rooks, so that there will be n rooks on the n by n chess table, and no two will fire to each other. There are n factorial ways to do that, as one can easily see, and you multiply it by plus minus 1 being sign of the permutation. And you can think of it either as a formula for determinant, or you can think of it as a way to think about sign. So it's kind of a generating function for sign. So in some sense, it's maybe for if you want to prove some more complicated properties of sign, it might make a lot of sense to look at this thing as a polynomial and to apply various algebraic tricks to it. And for instance, in homework, I will put a problem that if you take a determinant of a matrix 1 x1 to the x1 power n minus 1, and so on 1 x2 xn up to xn power n minus 1, you will actually get exactly this product we saw there. Product I less than j, I bigger than j, bigger equals than 1, lesser equals than n, xi minus xj. and this is called van der Monde determinant. And then this lemma becomes clear because it basically tells you that if you take determinant of your matrix and permute rows by sigma, you will get your determinant power minus 1 power sign. And that's a standard property of determinants. So it basically follows from properties of sign and computation of this particular determinant called van der Monde determinant. Okay, so here we end lecture 2.8, and the whole topic about permutation groups, we leave it for some time.